In this chapter, we will talk about further issues related to multiple linear regression analysis, and some of the topics we will cover here are, I guess, more frequently encountered when dealing with empirical data. So specifically, we will look at what happens when we scale our data, right? So if you're changing the units of measurements, whether of our dependent variable or independent variable, what happens to our OLS statistics, meaning our coefficients, the intercept or slope coefficients, and what happens to statistical inference, okay? Second, we will look at functional forms. So in particular, we will look at what happens when we take logs or incorporate quadratic terms or interaction terms, and when do those make sense. And finally, we'll close this chapter after talking about goodness of fit measures and how do we select which regressors to keep in our regression. So let's talk about the effects of scaling data on OLS statistics. Now, what do we know so far? So if we look at what we learned in the simple linear regression models, we had seen that if we change the units of measurement of the dependent variable, which is your y, or some of the independent variables, your x's, that is not going to change the interpretation of the OLS regression line. So something's always going to happen to the coefficients, but really what it implies is that if we rescale any of our variables, whether dependent or independent variables, the coefficients would change so that the interpretation is unchanged, okay? And I think what we can do is we can take a look at this regression right here and try to understand what would happen if we rescaled our variables. So let's start by making the first change, which is to the dependent variable y. So let's assume we want to change or scale our dependent variable y by a non-zero constant, c. Okay, so c is some non-zero constant. It could be 1,000, it could be 1,000,000, it could be anything, right? And if we multiply the left-hand side of this equation by c, for this equation to hold, you know that this entire right-hand side also has to be multiplied by c. So essentially what would happen is that each of these coefficients that you see, the intercept, the slope coefficients, all would be multiplied by c. Okay, so the intercept and slopes get multiplied by c. Okay, and now the question is, what would happen to the fitted values and residuals? The fitted values and residuals also get multiplied by c. However, what does not happen is any change to r squared. Okay, so the r squared is going to remain constant. Also, nothing happens to the t statistics. Okay, and in the lab, we'll see many examples of this. But if your c was negative, right, then the sign would be flipped of your t statistics. Okay, and similarly for f statistics, you're not going to see any change. Now, if we, instead of making this change, if we multiplied our independent variable xj, so let's take x1 for instance. Let's say that we multiplied x1 by c. Okay, what would happen is, for this equation to hold, beta 1 would be then divided by c, or beta 1 would be rescaled in a way so that the interpretation, this relationship between y and this new x1, does not change. Okay, so in other words, if we did this operation right here, then the coefficient in x1 gets divided by c. Nothing happens to the fitted values, remember, because this operation is sort of localized. It's localized because it's just happening here, right? Not changing the whole equation. Nothing happens to the residuals or R squared, okay? And also nothing happens to the T or F statistics. Only T statistics would change if you're multiplying xj by a negative value. Now let's take a look what happens if we have an equation like this where we have log y as our dependent variable. Okay, so everything else on the right hand side is pretty similar to before, but on the left hand side you have log of y. And what happens if we now do the same thing to y? So we were scaling y by the constant c, where c is strictly positive. And what that would do, so if you think about this left hand side becoming log of c times y, you can rewrite this in this way. So your left hand side is essentially, this becomes log of y plus log of c, okay? So it's almost like an adjustment that's happening on the left hand side. So earlier we just had log of y, but now there's some addition of some constant log of c on the left hand side. So again, for this equation to hold, this is going to be added also to the right hand side, okay? And so this essentially means that the intercept gets increased by log of c, okay? And you can take an example here and see what happens. So let's say we had y was income in thousands, right? So thousands of dollars. And now you want to change y to make it income in dollars, right? So now you want to change y and you just want this to be measured in dollars and not thousands of dollars. You would basically do this type of an operation where your new y is 1,000 times y, okay? And so when you take the logs, right, you're going to have two terms appear. You have log of 1,000 plus log of y. This is the same as before, but this is what gets added. So your intercept would just get increased by 6.91 in this case, okay? And here, none of the slopes, because this was so localized, none of the slopes would change for x1 and x2. The fitted values would increase by 6.91 and the residuals and R squared would not change, okay? Again, nothing would happen to T or F statistics. You can also think about what happens if we change the independent variable. Okay, so again, in that example where you said log of y equals, let's say this was a constant elasticity model where we had, okay, so this was our model, and now we are basically changing x1 and we are multiplying it by c. Okay, so c times x1 is our new x. And so notice here, the intercept, this can be written again as beta 1 times log of x1 plus log of c, right? And so this is, when you open up this term right here, this remains the same, but this changes, right? So this just gets added to the intercept, beta naught. And so the intercept would change, the coefficient on xj will not, right? This stays beta 1, just like before. And neither would the R squared or any test statistic like the T or F statistic would change, okay? So that only statistics related to the intercept would change. Okay, And so in the lab, we are going to look at this nice example where we can do a lot. So we can look at this data, which is called birth weight, BWGHT, and we would illustrate all of these points. Okay, so we would be looking at birth weight in pounds, which is birth weight divided by 16, if birth weight is originally measured in ounces. And what we're essentially trying to do with this data set is trying to predict birth weight based on smoking behavior of the mothers and family income. Okay, so here we can keep changing something about Y, whether we are changing the units of Y. So if earlier we were doing, measuring this in ounces, now we are measuring it in pounds. Or if we were measuring number of cigarettes before, we can also convert this into packs, right? So if one pack has 20 cigarettes, then we can do some sort of an analysis with this type of operation. And then if family income was measured in thousands of dollars, if family income was measured in thousands of dollars, we can see how that can be changed to just measuring family income in dollars, and how this operation would affect everything else. Okay, you would see that nothing unexpected would happen. Okay, whatever we described before would stay. So we cannot change. Ultimately, if we change the measurement or we scale our variables, we cannot change the importance of an effect. Right? So whether it's the effect of smoking on birth weight of a child, it's the essential underlying effect is not going to change with changing scales. Okay. Also, the goodness of fit will not change, and also the statistical inference will not change if we change the units of measurement. And really, that is the bottom line here. Now remember, we're going to move on to logs in the next segment, but change in logs is an approximation, and it gives us proportionate or percentage changes. But it has an advantage when we have a log-log model, for instance, because we can then measure elasticities that are absolutely free of units of measurement. Okay, so that's what you want to keep in mind.